Hello Info-Person, this is Anton, and very recently NASA announced that they finally completed a very exciting and somewhat important mission that placed a very unique atomic clock in space and essentially tried to see if this particular technology would work on a typical spaceship. With the atomic clock itself staying in orbit for approximately 2 years, doing all sorts of calculations. But the reason this particular mission is important is in regards to the potential future technologies when it comes to space navigation and essentially keeping track of where we are in space on some of the future missions, including the manned missions to various objects such as Mars. And so I wanted to discuss this in more detail and explain to you why this is sort of important. But I wanted to start right here, with the idea of timekeeping. Almost a year ago I made a video in regards to the most accurate clock ever made, that also went through some of the history of timekeeping, including some of the major inventions in the last few centuries. The video should be popping up somewhere right there, but one major takeaway from this particular video in regards to what we're talking about today is actually the reasons why, time and time again, we kind of had to improve our technology when it comes to the ability of keeping time. Most of the major advances in timekeeping actually came from the need for navigation. The need to know exactly where the boat is located, for example, by using the exact time that will be produced by a typical clock. And even today, this is really no different. GPS, for example, which is the most accurate navigation system we've ever produced, entirely relies on the idea of extremely precise timekeeping using extremely precise atomic clocks. And even though for decades the precision of a typical atomic clock was more than enough, today even that is no longer really acceptable. Some of the modern advances in atomic clocks have improved their accuracy by anywhere from just about 10 to 100 times up to about 1,000 times, such as this clock right here created by the scientists from the University of Colorado Boulder that uses strontium optical lattice to create such a ridiculous accuracy that this particular clock only loses 1 second every 15 billion years. And so today there's definitely a kind of a push for better and more accurate clocks, simply because we have new navigation needs and a lot of the systems need to be improved. Although I guess a quick side note, some of you might be wondering how exactly does the atomic clock work? What exactly does it do to function and to maintain such extreme accuracies? Well, just like with the pendulum clock or really any kind of a timekeeping device, it relies on oscillations. Something has to repeat many times in order for the clock to be able to detect differences. And generally speaking, most atomic clocks work in a very similar way. So first of all, they employ quartz crystals. When it comes to quartz crystals, they start oscillating if electric current is passed through them. But their oscillations are not really that high, and so they do end up losing a few seconds every few years. But back in 1955, Jack Perry and Louis Essen realized that they can actually use cesium atoms to create a kind of a feedback loop that's actually going to prevent the loss of seconds in the crystal oscillations. Now, the reason why cesium was chosen back in the days is really because of its structure when it comes to electrons. One of its outer orbitals has only one single electron in it. And because of this one electron right here, all cesium atoms start to oscillate between the low energy and the high energy state at an extremely precise frequency. And so, generally speaking, here's how all of this works. Both high energy and low energy cesium atoms are first filtered out using different magnets. The high energy atoms actually are not used at all, but the low energy atoms end up being stimulated using specific frequency. And once they're stimulated, they become high energy atoms. These high energy atoms are then moved into the detector that uses an electric current to sort of create a feedback loop with the quartz oscillator. And so if by some chance the quartz oscillator makes a mistake and starts to deviate from its natural oscillation, it actually shuts down this loop, which then forces the entire system to reset and to sort of kickstart the quartz oscillator once again. And so by using this relatively simple system, we've been successfully keeping extremely accurate time since the late 50s. And this is exactly how a lot of space scientists usually are able to tell exactly where the spacecraft is in a certain location in the solar system. The way it's done today is by essentially keeping extremely accurate atomic clocks on planet Earth and by beaming the signals to the spacecraft, which are then reflected from the craft and are sent back to Earth. And since we know the speed of light and we can also use the Doppler shift of the spacecraft to determine its speed, it thus becomes quite possible for the scientists to work out exactly where the spacecraft is located by extremely accurately measuring the distance between planet Earth and the spacecraft. But I guess one major problem here is really the distance. At closer distances, this works pretty well, but as you reach distances where the actual signal takes minutes or even hours to reach the spacecraft, and so in this case we're talking about deep space missions, trying to calculate the precise location of the spacecraft becomes a little bit more problematic. Now, some of the modern deep space missions, such as the New Horizons, also use a lot of other techniques, such as, for example, using the quasar map that can generally help them orient themselves and thus work out the precise location for a certain probe. This is, by the way, exactly what the New Horizons did approximately a few years ago in order to work out the precise navigation for one of the most recent rendezvous with the object known as the Arrokoth. And this right here is the map of quasars that's normally used by NASA and by a lot of different GPS systems. But once again, not super precise. As a matter of fact, even with these techniques, you'll still be off by a few thousand kilometers, assuming you're really far away from planet Earth. And so one of the possible solutions here is to actually put a very accurate atomic clock on the spacecraft itself. And so instead of relying on signals coming from planet Earth, you now have the actual atomic clock on board. And that's the mission that NASA was trying to investigate for the past 2 years. They placed an atomic clock in orbit around our planet. And they named this mission the Deep Space Atomic Clock, the picture of which you see right here. And finally, in September of 2021, it successfully completed its 2-year mission. And honestly, it's a pretty impressive device. First of all, the size of this box itself. It's really small. Apparently, it's only the size of a small toaster. Second of all, it was designed to survive a lot of different, very difficult conditions. And here we're talking about everything from the rocket launch to extremely cold conditions to obviously a lot of different types of radiation and magnetism in space, with the clock itself still staying pretty accurate even after years of operation. And more importantly, it solves one of the major problems with the atomic clocks here on planet Earth. This clock seems to be a lot more accurate, which is really important for deep space missions, mostly for one major reason. For example, a lot of GPS satellites rely on constant corrections approximately twice a day, mostly because of a slight deviation even in the atomic clocks and their measurement of time. But these types of corrections would be very difficult to achieve if a mission is what's known as a deep space mission, if the signal to the spacecraft takes anywhere from minutes to hours to reach it. And because of this, the accuracy degrades pretty quickly. To solve this problem, the NASA scientists decided to do something a little bit different. Instead of cesium atoms, they decided to use mercury ions. And they used ions in this case in order to use magnetic forces to prevent ions from the interaction with various walls of the clock itself, because by interacting with walls, they'll actually reduce the accuracy. And so by having these ions in a very specific location and by measuring their oscillation, after approximately 20 days of operation, the atomic clock only lost 4 nanoseconds, which by itself is extremely impressive. Which means that by placing one of these devices into a satellite, we can now achieve extremely accurate measurements of different types of position and even satellite speed. And so all of this is extremely important for some of the future missions, including manned missions to Mars. But before Mars, NASA is actually planning to try to test this in one of the future missions to Venus. Specifically the mission we discussed in one of the previous videos, somewhere right there. The mission is going to be launching in a few years, known as Veritas. And so the so-called Deep Space Atomic Clock 2, the slightly upgraded version of this atomic clock, is going to be inside the Veritas in order to test its accuracy of measurement and in order to see if it really works in an actual deep space mission. And considering the fact that this is going to be a multi-year mission, this is going to be one of the best opportunities to basically test the technology and to see if we can use this for future manned missions. Which means that we've come a full circle. The original implementations of the ancient clocks was to try to improve navigation using various sailboats, but now we're using new advances in timekeeping to try to improve space navigation, with some of the future clocks potentially being even more advanced to what we currently have. One of the propositions is actually to use optical clocks, so some of the future clocks are probably going to be using much higher frequency and different types of light that you can, in theory, even see. But we'll talk more about some of these advances in some of the future videos. Until then, check out the links in the description below, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support the channel on Patreon by joining the channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.